Good evening, it's Mr. Kaczynski. I've got your solutions to the Unit 8-3.2 checkup. Exploring growth patterns. The main thing we dealt with here in this investigation is starting values other than 1. So, let's get going here. Holiday Lake has a killer plant problem similar to Ghost Lake in problem 2.1. Currently, 4,000 square feet of the lake is covered with the plant, and the area covered is growing by a growth factor of 1.4 every year. So I guess the first thing I think about or read is this 4,000 square feet of the lake is covered with the plant currently, like right now. And even better yet, I should probably make this green, because I usually make our starting amounts green. So 4,000 right now. And then we've got a growth factor of 1.4. So I'm going to use my graphing calculator here. And if I do 4,000 and a growth factor of 1.4, I see that after 1 year, there's going to be 5,600 square feet of the lake covered. And if I just hit enter a few more times, I'll get weeks, or excuse me, year 2, year 3, year 4, and year 5. And I can just fill those into the table. So 7840 and 10,976, 15,366, and 21,513 square feet. And I just rounded those. So starting with 4,000, multiplying by 1.4 to get the area covered each year. Next, write an equation to model the area covered. All right, there we go. So we know that it's always the initial amount times the growth factor to the power of x, or in this case t, because I was told to use t for time, or the number of years that has passed. So 4,000 times 1.4 to the power of t. So what I did too is I went ahead and punched that into my calculator. There's the equation. And when I look at the table in the calculator, it should match the table that I've created over here. And it does. And if it doesn't match this table, if these two tables don't match, then I know I've got the wrong equation. So that's a great thing about having the graphing calculators. We can check that over and over until we get the right equation. Not that there's a lot to it. It's starting value times growth factor to the power of the independent variable. The following equation models the salary of a professional basketball player, S, after each complete season T in the league. I was very careful with my wording to put after each complete season. So in his first year under the contract, he hasn't completed a full season yet, so T would be 0. So how much will the player make in the initial season of the contract? Well, that's right there in the equation, $10,000. How much will the basketball player make after 1 season of his contract, or in the second season? Well, probably the easiest way to think about it is just, okay, there's my initial amount, 10,000. There's my growth factor 2. I'll just take 10,000 times 2, and that should give me the next year, $20,000. Growth factor of the equation, like I just mentioned, is 2. And what does that tell us about the salary of the player? We can tell that this means that the player's salary will double after each season. If the growth factor was 3, then the player's salary would triple after each season. And after how many seasons will his salary first exceed $5 million? So what I did is go ahead and plug this equation into the calculator, 10,000 times 2 to the power of x. Then I checked out the table, and I could see that it got to 5 million there when x was 9. So after 9 full seasons, which is actually in his 10th season, after 9 full seasons, or in his 10th season, he will have a salary that exceeds $5 million. Alright, so now we're given a table and we're asked to write an equation. Okay, so first of all, I can see the starting amount is 5. In fact, I'm going to go ahead and highlight that green. And I can also see that or pretty quickly identify that the growth factor is 3, because 5 times 3 is 15, 15 times 3 is 45, 45 times 3 is 135, so on and so forth. So that number and that number are all I need to write the equation. 5 times 3 to the power of x. I'd be silly not to check this on my calculator, so I type that equation that I just wrote into my calculator, bring up the table, and you can see that this table matches this table. The table in the calculator matches the table that was given to me. 5, 12, 15. There it is. 4, 405. So I know I've got the right equation. That's what that tells me. Next. This one's a little bit more difficult because we're not given a starting value. Okay, and some people identified it and thought that the starting value was 8, but the initial value is when x equals 0, what's y? So I guess let's concentrate first on the growth factor here. 8 times 4 is 32. So it looks like my growth factor is 4 if this is indeed an exponential function, which it is, because 32 times 4 is 128. 128 times 4 is 512. 512 times 4 is 2048, and that times 4 is 8192. So to figure out what y is when x equals 0, I should simply divide by 4. 8 divided by 4 is 2. And in reverse, 2 times 4 is 8. So now I've got everything I need. Okay, I know now that my initial amount is 2. My growth factor is 4. So it should be 2 times 4 to the power of x. Again, I can type that equation into my calculator. 2 times 4 to the power of x. Check out the table, and you see that that table does match what I've got here. 832, 128, 512, when x is 1, 2, 3, and 4. A population of rats has a growth factor of 5. After 1 month, there are 125 rats. After 2 months, there are 625 rats. How many rats were in the population initially? Well, they didn't really even need to give us the growth factor if they would have just told us it's exponential, but because I could have figured out the growth factor by doing 625 divided by 125 is 5. I also know that 625 divided by the growth factor of 5 is 125. So if I take month 2, divide it by the growth factor, that'll give me month 1. Also, if I take month 1 divided by the growth factor, that'll give me the initial amount of the population, which is 25 rats. So really, this was the only work we needed to do. I just showed this work to verify what I'm doing is correct. And also, if I wanted to find out month 3, I would just take 625 and multiply by 3. Gross. That's a lot of rats. All right, last problem here. George's parents give him a choice on how they will pay his allowance. If he chooses plan A, they're going to give him $1 the first week, then give him 4 times as much each week for 10 weeks. So I decided to make a table. And that table would look like this. Okay, so I'm going to give them $1 the first week and 4 times as much each additional week. I think some people wrote the wrong equation. They wrote y equals 4 to the power of x minus 1, or 4 to the power of x instead of 4 to the power of x minus 1, but it's actually 4 to the power of x minus 1. Because 4 to the first power is 4, not 1. So, at any rate, even if you were 1 off in your tables, you still should have been able to answer this question. Next, if he chooses plan B, they'll give him $4 the first week and then give him 2 times as much each week for 20 weeks. So you can see here after 10 weeks, yeah, I mean, plan A would be a lot better. But because plan B goes out to 20 weeks, it ends up being over $2 million. Again, $2 million is a lot more than $262,000. Either way, a very good allowance, but given the choice, I think I'd take the $2 million. And again, the equation for that, not that we needed it, was 4 times 2 to the power of x minus 1. So, in summary, George should choose plan B. In the 20th week, his parents will give him $2,097,000. $2,097,152. This is 8 times as much as he would receive in week 10 of plan A. Obviously, if we add all this up, actually if you add all this up of plan A, it won't even equal the 20th week. Whereas if you add all 20 weeks of plan B, I mean, you're over $3 million just in the last 2 weeks alone. Okay, whereas this won't even add up to $1 million. George's parents are loaded. Either way, he's looking good, but he should definitely choose plan B. That's all I've got for you tonight. Quick 10-minute video with the solutions. Hopefully you took the time to watch it and it helps with your corrections. See me with any questions, and have a great night.